A model can memorize rare training records, even when accuracy looks normal. Opacus applies DP-SGD and reports Epsilon, so privacy loss becomes measurable. You'll see how to connect the pieces into a workflow that trains with clipping and noise, then reports privacy cost beside accuracy. I'm Professor Pi, teaching AI foundations with simple Python. Data scientists train models on sensitive logs and health or finance records all the time. A correctly trained classifier can still leak an unusual record because gradients let that record steer updates. Differentially private training prevents that steering by bounding and obfuscating each record's influence. Opacus is a PyTorch library that plugs into the familiar training loop and gives you two things. It enforces per-sample gradient clipping, and it adds calibrated noise. It also produces an epsilon value, so the privacy cost is not a secret number you guess. Intuitively, we want every single training row to have limited power. Think of each gradient like a tug on a rope. Clipping cuts any tug that is too strong. Noise blurs the direction of small tugs, so individual pulls do not stand out. The privacy accountant watches how many noisy updates we perform and reports a privacy budget called Epsilon. Lower epsilon means stronger guarantee, but usually harder to learn. We will build a tiny example that makes records explicit, shows a non-private baseline, probes per-sample norms, then wraps the training loop with Opacus and reports epsilon next to accuracy. This keeps the ideas visible, so you can scale them later to a real dataset without losing the main decisions. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we make the training records explicit, so privacy statements are about concrete rows instead of an abstract pipeline. This snippet builds a tiny PyTorch dataset, so the privacy story is tied to explicit rows rather than hidden inside a large ETL pipeline. The tensor X holds one numeric feature per row. Y holds class labels, and tensor dataset pairs them, so data loader can batch them later. The seed keeps model init and noisy runs comparable on screen. The printed output shows the record count and class balance, which anchors every later accuracy and privacy cost number. Now we check how a plain model behaves, so we have a reference point for accuracy and loss before any private mechanism. This example trains a plain NN.linear classifier with ordinary SGD to give a non-private baseline for accuracy and loss. Data loader feeds the 6 records as one batch. Cross-entropy loss measures classification error, and opt step applies the usual gradient update with no clipping and no noise. That baseline shows how well the model can do when nothing limits per-sample influence. The output reports ordinary ACC beside last loss, which sets the reference to compare the DP version against. We need to know how much each record would change the update before we clip, so we inspect per-sample gradients. This code wraps the model with Opacus GradSampleModule, so we can inspect per-sample gradients instead of a batch average. Ordinary PyTorch gradients hide whether a single record is dominating the step. After backward, each parameter carries grad sample, and sample norms measures each record's update size separately. The threshold 1.0 previews the max grad norm we will give to DP-SGD. Lower values clip more, higher values let larger individual influence through before noise is added. The output shows the largest per-sample norm and how many records exceed the clipping line. Having measured norms, we now convert the optimizer and loader, so each optimizer step will clip individual gradients and then add noise. This snippet uses privacy engine make private to turn familiar PyTorch objects into their Opacus private versions, so optimizer steps will do DP-SGD. Passing DP model, DP opt, and loader back gives a training loop that looks the same, but where the optimizer clips per sample gradients to max grad norm, and then adds Gaussian noise scaled by noise multiplier. Increasing noise multiplier usually improves privacy accounting but makes learning noisier. Decreasing it can help utility but spends privacy faster. The output confirms a private batch was processed and reports the DP loss after one wrapped update. Finally, we complete the tiny run and make the privacy cost visible alongside performance. This example finishes a tiny Opacus baseline and makes utility and privacy visible together by calling privacyEngine.getEpsilon delta equals target delta after training. The loop keeps the same PyTorch shape as before, but dpopt is already the Opacus wrapped optimizer that clips and adds noise on each step. Target delta sets the failure probability side of the privacy statement and should be chosen deliberately for your dataset and policy. The output puts DP accuracy next to Epsilon, making the trade-off between utility and privacy explicit instead of implicit. If you move this toy into a real pipeline, replace the 6-row toy set with a real corpus like MNIST or a hospital cohort. Keep the same probing step to pick max grad norm, and choose target delta to match institutional policy. You will also tune noise multiplier to reach a useful epsilon for your downstream task and compliance needs. 3 quick takeaways. This trains with per record clipping and noise, so individual data points have limited influence. Use it when training on sensitive personal records where a numerical privacy statement matters. Remember that stronger privacy usually reduces utility, so expect a trade-off and plan validation accordingly. A useful next step is to scale this example to MNIST and sweep noise multiplier and max grad norm to find the best utility for an epsilon you can accept. That specific tuning is the fastest way to make this workflow production ready. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.